Tonight, we're going to unravel a contradiction that sounds almost impossible once you actually think about it. The sun is a nuclear furnace, so powerful that its surface alone sits at about 5,500 degrees Celsius. Its core burns at around 15 million degrees Celsius. And yet the space that sunlight travels through to reach us is not warm at all. It hovers just a few degrees above absolute zero, the coldest temperature physically possible. So how can something so relentlessly hot exist right next to something so profoundly cold, with nothing separating them but empty distance? By the end of tonight, you're going to understand why the sun can scorch your skin from 150 million kilometers away, while the space between here and there stays colder than anywhere on Earth has ever been. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with what you think you know about heat. You've felt it your whole life. You've held your hands near a fire and felt the warmth move toward you, even without touching anything. You've grabbed a metal railing in summer and pulled your hand away. You've stood in a shaft of sunlight coming through a window and felt the warmth on your face and arms. You've drunk a cup of tea and felt the heat move from the liquid into your throat. These experiences all feel like variations on the same thing: heat moving outward from something hot, spreading into the space around it, warming everything nearby. That instinct is real, and it's not wrong in everyday life, but it was built entirely in a world full of matter, full of air, full of surfaces and materials through which heat can travel in ways we never consciously notice. Space is almost completely empty, and in almost complete emptiness, heat barely travels at all. To understand why, you have to understand what heat actually is. Not what it feels like. What it is. At the most fundamental level, temperature is a measure of motion. Every atom and molecule in the universe is in constant motion. Every single one. Even the atoms that make up the chair you're sitting in right now are vibrating. Constantly. The atoms of the air around you are flying in every direction, bouncing off each other and off surfaces billions of times per second. In a solid, atoms are locked into a lattice structure by chemical bonds, but they're not still. They vibrate in place. They oscillate around their fixed positions with a speed and intensity that depends entirely on the temperature. At room temperature, the atoms in a piece of steel are vibrating about 10 trillion times per second. Each vibration moves the atom only a tiny fraction of a nanometer from its rest position. But 10 trillion oscillations per second at that scale adds up to a lot of kinetic energy. In a liquid, molecules have more freedom. The chemical bonds that hold them to a fixed position are gone. Molecules slide past each other. They tumble and flow. They're still in constant contact with each other, but they can rearrange and move through the material. In a gas, molecules travel in straight lines at high speed through open space until they collide with another molecule or a surface, then bounce off and travel in a new direction. In air, at room temperature, individual nitrogen and oxygen molecules are traveling at around 400 to 500 meters per second. Not the speed of sound, faster. The speed of sound in air, 343 meters per second, is approximately the average speed at which disturbances propagate through this constant molecular traffic. Individual molecules are actually moving faster than that. They just don't all go in the same direction at once. Temperature, at the most fundamental level, is the average kinetic energy of those particles. The faster they're moving on average, the higher the temperature. The slower they're moving, the lower the temperature. This is not a metaphor or an analogy. It's the literal definition of temperature at the microscopic level. Temperature is average kinetic energy per particle. It took a long time for humanity to work this out. For most of human history, heat was thought of as a substance, a fluid called caloric, in the dominant theory of the 18th century, that flowed from hot objects to cold ones, the way water flows from a high place to a low one. Objects contained more or less caloric. When caloric flowed into something, it got hotter. When caloric flowed out, it got colder. The theory had some appeal because it correctly predicted several things about how heat moves between objects in contact. But it had a serious problem. Count Benjamin Thompson, an American-born physicist working in Bavaria in the 1790s, noticed something while supervising the boring of cannon barrels. The boring process generated enormous amounts of heat. The metal shavings were hot. The water used to cool the process boiled away. The heat generated seemed to be essentially unlimited as long as the boring continued. Caloric theory had no good explanation for this. Where was all the caloric coming from? If caloric was a fluid stored in matter, why didn't the metal run out of it? Thomson suggested that heat was not a substance, but a form of motion. The mechanical work of boring was being converted into the motion of atoms. He was right. But it took decades more and contributions from James Prescott Joule, Rudolf Clausius, James Clerk Maxwell, and Ludwig Boltzmann before the kinetic theory of heat was fully worked out. By the late 19th century, the picture was clear. Temperature is motion. Heat is the total kinetic energy of that motion. And those two things are related but distinct. This distinction, which seems subtle at first, turns out to be the entire answer to the question we started with. If you understand the difference between temperature and heat, you understand why the sun can be millions of degrees and space can be 2.7 Kelvin simultaneously. You understand why the thermosphere can be 2,000 degrees and freeze you instantly. You understand why the space around a neutron star can be technically hot and still be cold. Temperature and heat are not the same, and space is the universe's most extreme illustration of why that matters. And those two things are related but distinct. The scale of those temperatures in everyday life gives you a sense of what the numbers mean. At room temperature, around 300 Kelvin, a nitrogen molecule in air is moving at about 500 meters per second. At the surface of the sun, around 5,800 Kelvin, if you could somehow have a free hydrogen atom there, it would be moving at about 10 kilometers per second. At the sun's corona, at 1,000,000 Kelvin, protons are moving at several hundred kilometers per second. These are not metaphorical speeds. They are the actual velocities of actual particles, measured by instruments, confirmed by observation. The temperature scale, from absolute zero to the corona of the sun, spans a factor of about 300 million. From the quantum mechanical silence of near zero Kelvin to the violent million-degree plasma of stellar atmospheres. And all of it is just particles moving, faster and faster, until the collisions between them become energetic enough to strip electrons from atoms, to fuse nuclei together, to create the conditions where stars are born and shine. The Kelvin scale was built directly on this understanding, proposed by the physicist William Thomson, later known as Lord Kelvin, in the 1840s and formalized over the following decades. The scale starts at absolute zero, the lowest temperature the universe permits. The temperature at which the thermal motion of particles is theoretically at its minimum, not zero motion in the quantum mechanical sense. The uncertainty principle forbids that. But the minimum, consistent with quantum mechanics. the lowest possible temperature. In Celsius, absolute zero sits at minus 273.15 degrees. At that temperature, all chemistry effectively halts. Thermal processes stop. The only energy particles retain is their quantum mechanical zero-point energy, which cannot be extracted as heat. The laws of thermodynamics, specifically what's called the third law, make it impossible to actually reach absolute zero. You can approach it. Laboratories have cooled small systems to within billionths of a degree, within a few millionths of a Kelvin, using techniques involving laser cooling, magnetic trapping, and evaporative cooling that would have seemed like science fiction a century ago. But the floor is there, and you can approach it only asymptotically. You can never quite arrive. Now consider the actual numbers in play here. The temperature of the void between star systems is about 2.7 Kelvin, 2.7 degrees above absolute zero, barely above the floor. The surface of the Sun is about 5,778 Kelvin. That's more than 2,000 times hotter than the interstellar void. The Sun's corona, its outermost atmosphere, reaches temperatures above 1 million Kelvin across most of its extent. In regions of intense activity, flaring regions above sunspots where magnetic energy is released violently, temperatures exceed several million Kelvin. So, we have an object measured in millions of degrees, surrounded by space at 2.7 degrees, separated by 150 million kilometers of near nothing. And that near nothing stays near frozen. The question is why? And the answer begins with three mechanisms. Only three mechanisms exist for moving heat from one place to another. Two of them don't work in space at all. There are exactly three ways heat can transfer: conduction, convection, radiation. Understanding what each of these physically requires is the key to the whole question. Conduction happens when things are in contact. When you touch a hot pan, the heat you feel is energy transferring from the fast-moving atoms of the pan into the slower atoms of your skin. At the atomic level, what's happening is this. The particles in the hot material are moving faster than the particles in the cooler material. At the interface where the two materials meet, faster-moving particles from the hot side collide with slower-moving particles from the cool side. Those collisions transfer kinetic energy. A fast particle slows slightly. A slow particle speeds up slightly. Energy moves from the hot side to the cool side. This happens trillions of times per second at every contact surface. And through this cascade of microscopic collisions, thermal energy flows from higher temperature to lower temperature. Always in that direction. Never the other way, on its own. Different materials conduct heat at radically different rates. Copper is one of the best conductors. If you hold a copper rod with one end in a flame, your fingers at the other end will feel heat in seconds. Copper has a thermal conductivity of about 400 watts per meter per Kelvin. That means that across 1 meter of copper, 1 watt of thermal power flows for every 1 degree Celsius of temperature difference between the two ends. Metals in general are good conductors for a specific reason. In metals, the outer electrons of each atom are not bound to their own atom. They're shared. They form what's called a sea of free electrons that can move throughout the entire metal structure. These free electrons carry kinetic energy and move rapidly from hot regions to cold regions of the metal, transferring that energy as they go. This is why metals feel cold when you touch them at room temperature. They're not actually colder than the wooden desk beside them. They're the same temperature. but the metal conducts heat away from your skin far more rapidly than the wood does. Your skin temperature drops faster than your body can replenish it. The skin gets colder. You perceive that local cooling as the metal being cold. It's a sensation of rapid heat loss, not actual temperature difference. Wood, plastic, stone, and foam are poor conductors. Their atomic structures don't allow kinetic energy to pass efficiently from atom to atom. Each atom barely communicates its vibration to its neighbors. The energy stays local. This is why a wooden handle on a pot doesn't get hot, even when the metal pot body is steaming. The wood is insulating, conducting the heat only very slowly. Air is also a relatively poor conductor. Air molecules transfer energy only through direct collisions with surfaces or with each other, and they're spread out enough that this is slow and inefficient compared to solid materials. But the absolute requirement for conduction is this: particles have to be close enough to collide. There must be a continuous chain of matter from the hot object to the cool one. If there's a gap, if the space between two objects contains nothing, the chain breaks. Energy has no way to jump the gap. Conduction stops. In the vacuum of space, this chain doesn't exist between separate objects. The solar wind, the stream of charged particles the sun continuously sheds into the solar system, does carry some particles through the inner solar system. At Earth's distance from the sun, the solar wind density is roughly 5 to 10 protons and electrons per cubic centimeter. At first hearing, that sounds like it might amount to something. It doesn't. Air at sea level contains about 27 million molecules per cubic centimeter. The solar wind is roughly 5 billion times less dense than the air you're breathing right now. At that density, the chance of any given solar wind particle colliding with any given surface in a meaningful amount of time is infinitesimally small. The rate of heat transfer through those extremely rare collisions is not just small, it's effectively unmeasurable. There simply aren't enough particles. They're not close enough together. The chain of collisions that conduction requires cannot sustain itself through a near-perfect vacuum. Conduction across the void of space is, for all practical purposes, zero. This is not because something is blocking the conduction. It's because there is almost nothing to conduct through. Conduction requires a chain of atoms. Space has almost none. The chain doesn't exist. There's a useful everyday illustration of why. A thermos flask keeps hot drinks hot and cold drinks cold using exactly the same principle. A thermos has two walls separated by a vacuum layer. That vacuum layer prevents conduction. There are no particles touching both the inner wall and the outer wall simultaneously. No chain of atoms to carry kinetic energy from one surface to the other. The inner wall might be at 80 degrees Celsius. The outer wall at room temperature. In between, a millimeter-thick vacuum. And that thin vacuum is almost as effective an insulator as the endless vacuum of space. This is why thermoses keep drinks warm for hours without any power source. No conduction through the vacuum layer. Only radiation at the walls themselves, which is relatively slow. Space achieves the same effect as the thermos vacuum, just over enormous distances. No particles means no conduction, and space has so few particles that the microscopic amount of conduction that could theoretically happen is irrelevant to any real thermal situation. Convection requires a fluid, a gas or a liquid that can flow and carry thermal energy in bulk from one place to another. When you heat the bottom of a pot of water, The water near the heat source warms first. Warm water expands slightly, becoming less dense than the surrounding cooler water above it. The warmer, less dense water rises. Cooler, denser water from above descends to take its place at the bottom. A circulation pattern forms. Convection cells. Rising columns of warm fluid. Sinking columns of cool fluid. The churning continues until the entire volume of water reaches the same temperature. You can make this process visible by dropping a tiny amount of food dye into a transparent pot of water being heated from below. The dye traces the convective currents, rising from the bottom, spreading across the top, sinking down the sides, constantly in motion, constantly distributing heat. The same process operates in Earth's atmosphere. Warm air near the heated surface rises. Cooler air from higher up descends to replace it. This creates the large-scale atmospheric circulation patterns that drive all weather on Earth. The trade winds, which blow reliably from east to west across the tropics, are powered by convection. Hot air rises at the equator, flows toward the poles at altitude, cools, sinks at around 30 degrees latitude, and returns along the surface back toward the equator. This atmospheric conveyor belt, and its various local and global variations, is responsible for the rain, the wind, the storms, the climate patterns that define every ecosystem on Earth. In the oceans, the same principle drives the thermohaline circulation, a global system of deep ocean currents driven partly by temperature differences and partly by salinity differences. Warm surface water moves from the tropics toward the poles. It cools. It becomes denser. It sinks to the deep ocean floor. It flows back toward the tropics along the bottom. This oceanic conveyor belt moves an enormous amount of heat around the planet. It's responsible for making Western Europe far warmer than it would otherwise be for its latitude. London sits at roughly the same latitude as Calgary in Canada. But London has mild, wet winters, while Calgary gets buried in snow. The Gulf Stream current carries warm tropical water across the North Atlantic and keeps the Western European climate significantly warmer than it would otherwise be. All of this, from trade winds to ocean currents, is convection driven by solar heating, creating temperature differences in fluids. Inside the sun itself, convection is critically important. The outer, roughly 30% of the sun's radius, in terms of mass, forms what's called the convection zone. Hot plasma rises from deep inside the sun in enormous columns that dwarf anything imaginable on Earth. A single convective cell in the sun can be larger than the entire Earth. The hot plasma rises, reaches the photosphere, the visible surface, and releases energy as radiation. It cools slightly. The slightly cooler plasma then sinks back down into the interior to be reheated. This process, repeated endlessly across the entire surface of the sun, is visible as granulation. If you look at the sun through a solar telescope with appropriate filters, the surface appears covered in a fine pattern of bright spots and slightly darker borders. Each bright spot is the top of a rising column of hot plasma. Each darker border is where slightly cooler plasma is descending. These granules are each roughly 1,000 to 2,000 kilometers across. They form and dissolve over a period of about 10 minutes. The entire sun's surface is covered by millions of them at any given moment, constantly forming, shifting, splitting, and merging. Convection shapes everything about the sun's visible appearance. But convection stops at the photosphere. The photosphere is the thin layer where the plasma becomes transparent, where photons can escape freely rather than being immediately reabsorbed. Below it, matter and energy are tightly coupled. Above it, light and matter decouple. The moment you cross out of the sun's atmosphere and into space, there is no fluid. There is no continuous medium for bulk flow. Convection cannot operate in a vacuum. The energy that reaches the photosphere through convection from below must find another path outward. Only one path remains: radiation. And radiation works in a completely different way from conduction and convection. It doesn't need anything between the source and the target. Not air, not fluid, not a single particle. It crosses the void as electromagnetic waves, as photons, traveling at the maximum speed the universe allows, 300,000 kilometers per second. No delay, no medium, no intervening chain of collisions. Just the direct propagation of energy through empty space. But that directness comes with a consequence that changes everything. Radiation is the only form of heat transfer that works without a medium. It doesn't need particles in contact. It doesn't need a fluid. It propagates through vacuum just as naturally as through anything else. In fact, electromagnetic radiation travels at its maximum speed, 300,000 kilometers per second, in a perfect vacuum. Any material it enters slows it down. Glass, water, air, all reduce the speed of light to some degree. Only a vacuum lets it travel at full speed. Every object in the universe above absolute zero emits electromagnetic radiation. Every one. This is a fundamental consequence of the physics of charged particles. Atoms are made of charged particles, protons, with positive charge in the nucleus, electrons with negative charge orbiting around it. When charged particles accelerate, they emit electromagnetic radiation. This is not a special case or an approximation. It's a fundamental consequence of Maxwell's equations of electromagnetism. Accelerating charged particles emit radiation, and at any temperature above absolute zero, atoms are in motion, vibrating, oscillating, colliding. All of this motion involves constant changes in velocity. Changes in velocity mean acceleration. Acceleration of charged particles means electromagnetic radiation. Everything above absolute zero is glowing. The question is just in which part of the spectrum. The spectrum of thermal radiation emitted by an object depends entirely on its temperature. This relationship, called black body radiation, was one of the great puzzles of 19th century physics. Physicists knew that hot objects glowed. They could measure the spectrum of that glow, but they couldn't derive the shape of that spectrum from the physics they knew. Every attempt using classical physics produced a result called the ultraviolet catastrophe. The equations predicted that objects should emit infinite energy at short wavelengths. Obviously wrong. Obviously, physically impossible. The resolution came in 1900. Max Planck, working on the problem intensely, found a mathematical formula that fit the observed spectra perfectly. But the formula required something radical. It required assuming that energy was not emitted continuously in arbitrary amounts. It was emitted in discrete packets, chunks, quanta. The energy of each quantum of radiation was proportional to the frequency of the radiation. High frequency, high energy. Low frequency, low energy. Planck wasn't sure what to make of this. He considered it a mathematical trick, not a physical reality. Albert Einstein, 5 years later, took it seriously and showed that light itself was quantized. That electromagnetic radiation came in discrete packets called photons. Each photon carries a specific amount of energy determined by its frequency. And the consequences of this for understanding heat in space are enormous. At low temperatures, objects radiate primarily in the infrared. Long wavelengths, low frequency, low energy per photon. Your body, at 37 degrees Celsius, radiates infrared light. You are glowing right now. You just glow at wavelengths human eyes cannot see, roughly in the range of 9 to 10 micrometers wavelength. Deep infrared. Thermal imaging cameras detect exactly this. They reveal people as bright, warm shapes against a cooler, darker background. Every warm body constantly emitting infrared. As temperature increases, the peak wavelength of emitted radiation shifts toward shorter wavelengths and higher energies. This relationship is described by Wien's displacement law, named after Wilhelm Wien, who derived it experimentally in the 1890s. The peak wavelength in micrometers is approximately 2,900, divided by the temperature in Kelvin. At room temperature, about 300 Kelvin, the peak is at about 10 micrometers, infrared. At 700 Kelvin, the peak shifts to about 4 micrometers, still infrared, but shorter. The object is also emitting some light at the very red end of the visible spectrum. Around 900 Kelvin, the emission in the red visible spectrum becomes significant. Objects start visibly glowing red. A metal heated in a forge. The element of a stovetop burner at high heat. Around 2000 Kelvin, the color shifts to orange. Around 2500 to 3000 Kelvin, the glow becomes white, mixing multiple colors of the visible spectrum. This is approximately the temperature of a traditional incandescent light bulb filament. The sun's surface, at 5778 Kelvin, emits across the entire visible spectrum. Its peak emission by Wien's law falls at roughly 500 nanometers wavelength, which is green light. But because the sun emits strongly from ultraviolet all the way through infrared, the mixture of all those wavelengths integrates to white light. That's why sunlight, spread through a prism, reveals a continuous rainbow. All wavelengths present, dominated by yellow-green in peak intensity. But all colors there. The sun radiates continuously. Ultraviolet. Visible light across all colors. Infrared. Radio waves. X-rays. Every part of the electromagnetic spectrum, all produced by the same mechanism. Charged particles in thermal motion, emitting radiation, all traveling outward from the sun's surface at the speed of light, in every direction, simultaneously. Real photons in staggering numbers, traveling outward from the sun's surface at 300,000 kilometers per second in every direction simultaneously. These photons carry real energy. They cross space. When they strike a surface, they're absorbed, and their energy heats that surface. This is exactly how the sun warms Earth, not through conduction, not through convection, through the absorption of photons that left the sun's surface and crossed 150 million kilometers of vacuum in 8 minutes and 20 seconds. So the sun does emit radiation that crosses space. And that radiation does heat things. It strikes. The question remains, why doesn't it warm space itself? Why, after 4.5 billion years of pouring radiation outward in every direction, Is the surrounding space still barely above absolute zero? Part of the answer is geometry. When the sun emits radiation, it doesn't aim it anywhere in particular. It emits it in all directions simultaneously, outward in an expanding sphere. Think about a light bulb. It emits light in all directions. Hold your hand close to the bulb, and the light on your palm is bright. Move your hand farther away, and the same number of photons per second that left the bulb are now spread across a larger sphere. Your palm intercepts fewer of them. It's dimmer. Move twice as far away, and the sphere the light is spread across has 4 times the surface area. Your palm receives 1/4 of the photons per second per unit area. Move 3 times as far away, and the sphere has 9 times the surface area. Your palm receives 1/9. This is the inverse square law. Intensity drops by the square of the distance from the source. At Earth's distance from the Sun, roughly 150 million kilometers, the solar radiation hitting each square meter of surface perpendicular to the incoming light is about 1,361 watts. This is the solar constant, a significant amount of power, enough to run a hairdryer on every square meter of sunlit surface facing the sun. At twice Earth's distance, that drops to about 340 watts per square meter. At 3 times Earth's distance, it drops to about 150 watts. The numbers fall steadily and relentlessly. By the time solar radiation reaches the heliopause, the boundary where the sun's influence gives way to interstellar space. At roughly 100 astronomical units from the sun, the intensity has fallen to about 0.1 watts per square meter, about 25,000 times weaker than at Earth. By the time it reaches the nearest star, Alpha Centauri, at 4.2 light-years away, the sun's radiation is diluted by a factor of nearly 250 trillion compared to its intensity at Earth, completely lost against the background of the universe. The inverse square law explains why the outer solar system is so cold and why interstellar space receives essentially nothing from the sun. But it doesn't answer the question about the space close to the sun. The inner solar system, between Mercury and Earth, is flooded with intense solar radiation. Photons are crossing that region by the trillion every second. Why doesn't that space warm up? To answer this precisely, it helps to understand what electromagnetic radiation is. Light is not a substance that flows like a fluid. It's a disturbance in the electromagnetic field. When a charged particle accelerates, it creates ripples in the electric and magnetic fields around it. These ripples propagate outward at the speed of light. They carry energy. They carry momentum. But they don't interact with the field itself while they travel. They don't lose energy to the medium they traverse. They don't deposit heat along the way. They travel until they strike matter. And in vacuum, matter is almost never there to be struck. A photon from the sun can travel 150 million kilometers and arrive at Earth's atmosphere carrying exactly as much energy as it had when it left the sun's surface. The space it traveled through is unchanged. The photon passed through as if the space weren't there. Because, in a sense, the space wasn't there. Vacuum is not a substance. It's an absence. And an absence doesn't absorb energy. Radiation doesn't heat vacuum. It can't. This is the most important single fact in this entire question. Vacuum has no particles to absorb radiation. A photon traveling through empty space doesn't lose energy to the vacuum. It doesn't interact with the vacuum. It doesn't slow down. It doesn't deposit energy anywhere. It travels. That's all. If it never encounters anything, it just keeps going, at full energy, at full speed, forever, in principle. Heating, nothing. Warming, nothing. Changing, nothing in the space it passes through. To understand why this is, it helps to understand what vacuum really means. Vacuum doesn't mean nothing. Not exactly. It means an absence of matter. But even in the best vacuum we can create in a laboratory, there are still some particles. The best laboratory vacuum chambers achieve pressures of around 10 to the power of -13 pascals. That still means roughly a few hundred molecules per cubic centimeter remain. Space is better than any laboratory vacuum we can create. In the inner solar system, the main source of particles is the solar wind. The roughly 5 to 10 protons and electrons per cubic centimeter that flow outward from the sun. Outside the solar system, in the interstellar medium, average density is around 1 atom per cubic centimeter. In the voids between galaxy clusters, the density drops further still, to around 1 atom per cubic meter, or lower. For a photon crossing these regions, the probability of encountering a particle is extraordinarily small. A single photon could travel millions of light-years through interstellar space before encountering a single atom. Through all of that journey, the photon isn't interacting with anything. It carries its energy through empty space. Electromagnetic fields don't interact with themselves in the classical sense. Light passes through light without scattering. One beam of sunlight can cross another beam of sunlight with no effect on either. The vacuum doesn't absorb the beams. The photons don't lose energy to the vacuum. A photon, traveling through interstellar space for 1,000,000 years, arrives at its destination, carrying exactly as much energy as it started with. Nothing deposited along the way. Nothing changed in the space it traveled through. As cold when it left as when it arrived. This is why you can see stars billions of light years away. Their light crosses billions of light years of space without being absorbed by the space it travels through, without losing its energy. If space absorbed radiation, the universe would go dark very quickly. Distant stars would fade as their light was absorbed before reaching us. We can see galaxies 10 billion light years away, precisely because space is transparent, because radiation crosses it without depositing energy in it. And that same transparency, that same inability of vacuum to absorb radiation, is exactly why the sun's radiation doesn't warm the space it crosses. The photons pass through. The space stays cold. The sun has been radiating for 4.5 billion years. Trillions upon trillions upon trillions of photons have crossed the inner solar system in every direction. They've passed through the same regions of space billions upon billions of times. And those regions of space are still at 2.7 Kelvin. Not slightly warmer than 2.7. Not warmed, even by a fraction of a degree, over 4.5 billion years. The same temperature as the deep void between galaxies, because the photons didn't interact with the space. The space didn't absorb them. They passed through without leaving anything behind. But space isn't perfectly empty. There are particles out there, the solar wind, the interstellar medium, sparse clouds of gas and dust. These particles do interact with radiation. They do absorb some photons. Don't they get hot? And if they get hot, doesn't that warm space? Here is where the most important distinction in this entire question comes in. The distinction between temperature and heat. These are two entirely different quantities. Temperature is the average kinetic energy per particle. Heat is the total thermal energy stored in a system. They are related, but in very sparse environments, they come wildly apart. Consider a single hydrogen atom that absorbs an energetic photon from the sun. The photon's energy excites the atom. The atom emits the energy as a new photon and recoils from the momentum of that emission. Its kinetic energy has increased. If you calculated the temperature implied by that atom's kinetic energy, you might get a number in the tens of thousands or even millions of Kelvin. Technically, by definition, that atom is at a very high temperature. But it's one atom, one particle. The total thermal energy stored in one atom is essentially nothing. If that single high-energy atom collided with your skin, it would deposit an amount of energy so infinitesimally small that no instrument on Earth could measure the resulting temperature change. You would not feel it. Not in a billion years of such collisions. Because you'd need enormous numbers of fast-moving particles colliding with a surface every second to transfer meaningful heat. In interstellar space, the density is roughly 1 hydrogen atom per cubic centimeter. Air at sea level contains about 27 million molecules per cubic centimeter. The interstellar medium is 27 million times less dense than air. Even if every interstellar atom were traveling at millions of Kelvin worth of kinetic energy, the total heat they could deliver to any surface per unit time would be negligible. The atoms are there. They're technically hot. They carry almost no heat. And when a spacecraft enters such a region, its own thermal radiation outward into the void far exceeds the rate at which those sparse hot atoms deliver energy through their rare collisions. The spacecraft cools, not heats, despite technically being immersed in hot gas. High temperature, almost no heat. This is one of the most important and most commonly missed distinctions in all of thermodynamics. Temperature tells you how fast the particles are moving. Heat tells you how much total energy is stored. A hot but empty room and a cool but full room are completely different thermal environments. Even if the individual molecules in the empty room are moving faster than those in the full room. This principle has a perfect illustration in Earth's own upper atmosphere. There's a layer called the thermosphere. It extends from about 80 kilometers above the surface to roughly 700 kilometers. Right at the edge, where Earth's atmosphere gives way to the near vacuum of space. And it is, by the technical definition, extremely hot. During periods of high solar activity, temperatures in the thermosphere reach above 2,000 degrees Celsius. In some conditions, depending on solar activity, even higher, 2,000 degrees Celsius. That is hotter than the melting point of iron, hotter than molten lava pouring from a volcano, hotter than the inside of a glass-making furnace. If you told someone that a layer of gas just a few hundred kilometers above their head was 2,000 degrees, their instinct would be that it would be utterly hostile, an inferno, something that would destroy any exposed surface. And yet, if you were somehow suspended in the thermosphere without a spacesuit, you would not feel heat. You would feel cold. Your body would be losing heat faster than it could possibly gain any. The thermosphere is technically hot because the sparse molecules up there are absorbing extreme ultraviolet and X-ray radiation from the sun. This radiation has enormous energy per photon. When those energetic photons hit sparse thermospheric molecules, the molecules absorb that energy. They are driven to very high kinetic energies. They move fast, very fast. Average kinetic energy per particle is high. Temperature which is defined as average kinetic energy per particle, is correspondingly very high, 2000 degrees Celsius. But the density of the thermosphere is extraordinarily low. At 80 kilometers altitude, the atmospheric density is already about 100,000 times lower than at sea level. At 400 kilometers, the altitude at which the International Space Station orbits, atmospheric density is roughly 10 billion times lower than at sea level. There are so few molecules that even though each one moves fast, the actual rate at which they collide with any surface is vanishingly small. The collisions are rare. The energy exchanged through them even rarer. Almost nothing. Almost no heat at all. The number of molecules striking a square centimeter of surface per second in the thermosphere is a tiny fraction of what it would be at sea level. And heat transfer by molecular collision depends entirely on how many collisions happen per second and how much energy each one transfers. With barely any collisions per second, almost no heat is transferred. Meanwhile, your body radiates infrared energy outward continuously. The rate of energy loss from your own thermal radiation vastly exceeds the rate at which those sparse hot molecules deliver energy. You would cool down, despite being surrounded by technically 2000-degree gas. The thermosphere is a perfect illustration of the paradox at the heart of this whole question. High temperature and almost no heat. The aurora borealis, the northern lights, happens in the thermosphere. Charged particles from the sun, electrons and protons in the solar wind, are funneled by Earth's magnetic field toward the polar regions. They collide with the sparse thermospheric molecules and ions. These collisions excite the atmospheric particles, knock electrons into higher energy states. The electrons drop back down to lower energy states and emit visible light in the process. Green, from oxygen, at about 100 kilometers altitude. Red from oxygen at higher altitudes. Blue and purple from nitrogen. The result is those curtains of shimmering light visible from high latitudes. Beautiful. And produced entirely in gas that is technically at temperatures far above the melting point of steel, but cold enough to freeze you in seconds. Because temperature without density is just a number. There's a precise way to express the difference between temperature and heat. In physics, the heat content of a gas depends on both temperature and number of particles. Specifically, the total thermal energy of a gas is the number of particles multiplied by Boltzmann's constant multiplied by the temperature. Boltzmann's constant is roughly 1.4 times 10 to the power of minus 23 joules per Kelvin. Very small. But multiply it by the enormous number of particles in everyday matter, and you get the macroscopic heat energy we experience. A cubic meter of air at room temperature, around 300 Kelvin, contains roughly 27 million molecules. Total thermal energy, about 43 kilojoules, enough to run a small light bulb for several minutes. A cubic meter of the hot ionized medium of the interstellar medium at 1,000,000 Kelvin contains roughly 1 proton. Total thermal energy, roughly 10 to the power of minus 17 joules. A 10 millionth of a billionth of a joule. The hot interstellar gas at 1,000,000 Kelvin contains roughly 27 million, trillion times less thermal energy per cubic meter than room temperature air. High temperature, no heat. The numbers don't care about the intuition. They just describe what's there. The sun's corona makes this point in an even more dramatic way. The photosphere of the sun, the visible surface, is at about 5,778 Kelvin. Above that, the corona. the Sun's outer atmosphere extends millions of kilometers into space. During a total solar eclipse, when the Moon perfectly blocks the Sun's bright disk, you can see the corona, a pale, ghostly halo. Streamers and loops extending far beyond the Sun's limb, delicate and beautiful. And that halo is hotter than the surface below it, dramatically hotter. Temperatures in the corona exceed 1 million Kelvin throughout most of its extent. In the most active regions, above sunspots where the magnetic field is strongest and most complex, temperatures reach several million Kelvin. This deeply puzzled physicists when it was first properly measured in the 1940s and 50s. The discovery came from spectroscopy. Astronomers studying the light from the corona found spectral lines that couldn't be attributed to any known element. For a while, scientists wondered if they were seeing a new element, which they called coronium. Eventually, the mystery was solved. The lines were from familiar elements, but observed under such extreme conditions that the atoms had lost most of their electrons. Highly ionized, iron, and other metals. The ionization state revealed the temperature. To strip an iron atom of 13 or more of its electrons requires temperatures above 1 million Kelvin. The corona was that hot. This was enormously puzzling. Everything in thermodynamics says temperature should decrease as you move away from the energy source. Earth's atmosphere gets colder as you go higher. The air above a candle flame is not hotter than the flame itself. Energy flows from hot to cold, not from cold to hot. So, why is the Sun's outer atmosphere hotter than its surface? This is called the coronal heating problem, and it has occupied solar physicists for decades. The current best understanding involves magnetic energy. The Sun's magnetic field is generated deep in its interior by the motion of electrically conducting plasma. It's turbulent, complex, full of braided, tangled field lines. As the solar surface churns and convects, it constantly twists and stresses these field lines. Waves called Alfvén waves, a type of wave that propagates along magnetic field lines like vibrations along a string, carry energy upward from the turbulent photosphere into the corona. As these waves reach the increasingly thin corona, they encounter different plasma conditions and dissipate. They deposit their energy as heat. In addition, intense events called magnetic reconnection contribute enormously. When magnetic field lines of opposite polarity are forced together, they can suddenly snap and reconnect in new configurations. This releases the stored magnetic energy explosively. The energy goes into heating and accelerating the local plasma. The largest reconnection events are solar flares, visible as sudden brightenings of specific regions of the Sun, releasing in minutes the energy equivalent of billions of nuclear weapons. Smaller, more frequent reconnection events heat the corona continuously and in a more distributed way. Both mechanisms together drive coronal temperatures to 1 million Kelvin and above. The mission Parker Solar Probe, launched in 2018, has flown closer to the Sun than any previous spacecraft, sampling the corona directly, measuring plasma properties, magnetic fields, and particle energies at distances that no spacecraft had reached before. It has helped confirm and refine our understanding of how the corona is heated, including direct detection of switchbacks, sudden reversals in the solar magnetic field that may contribute to energy transfer and coronal heating. But again, here's the point for our question. The corona is at 1 million Kelvin. It extends into the space around the Sun. Doesn't that warm the space around the Sun? No. For exactly the same reason, the thermosphere doesn't warm the space around Earth. The corona is at 1,000,000 Kelvin and extraordinarily thin. The density of coronal plasma is millions of times lower than the photosphere. The photosphere is already millions of times less dense than air. The outer corona is essentially nothing. Almost no particles. Almost no heat content. High temperature. Essentially, no heat. The space around the Sun is bathed in coronal plasma that is technically at 1,000,000 Kelvin. And that space is still near absolute zero. Because the particles carrying that technical temperature are so sparse that they're not actually putting meaningful heat into anything. Some extreme examples outside our solar system make this even clearer. Neutron stars are some of the hottest objects in the universe. The remnant cores of massive stars that exploded as supernovae, compressed to about 20 kilometers in diameter, with surface temperatures that can exceed 1,000,000 Kelvin when they're young. Some neutron stars, pulsars, are spinning hundreds of times per second. They emit beams of radio waves, X-rays, and gamma rays that sweep across space like cosmic lighthouses. And yet, the space around a neutron star is still cold. The neutron star is radiating intensely. Its photons cross the surrounding space. But without a medium to absorb the radiation, without dense matter nearby, the space around a neutron star remains at 2.7 Kelvin, plus whatever diluted stellar radiation happens to be passing through. The neutron star's heat stays in its own body. It radiates outward. The photons cross the void. And the void, as always, remains cold. Only the surfaces that absorb those photons, other stars, gas clouds, spacecraft instruments, are warmed. The space between is unchanged. The solar wind extends this thinning outward through the solar system. The corona doesn't have a sharp edge. It transitions smoothly into the solar wind. The Sun's gravity and its magnetic field structure the corona into a complex shape, with streamers and equatorial regions and polar regions of different properties. In some directions, particularly near the poles during quiet solar conditions, the corona expands rapidly along open magnetic field lines, creating what's called the fast solar wind. Streams of particles traveling at 600 to 800 kilometers per second. Near the equator, the solar wind tends to be slower, 300 to 500 kilometers per second. Both fast and slow solar wind are still flowing outward through the solar system, past Mercury, past Earth, past Mars, filling the heliosphere, the bubble of solar influence carved out by the Sun in the interstellar medium. At Earth's orbit, the solar wind carries about 5 to 10 particles per cubic centimeter. Temperatures around 100,000 Kelvin. Still technically very hot. Still far too sparse to warm anything in a meaningful way. A spacecraft in orbit is not heated by the solar wind. It's heated by absorbing solar photons. The photons carry far more energy than the particle wind. But the photons don't warm the space either. They warm the surfaces that absorb them, not the space between those surfaces. The cosmic microwave background sets the floor. This is the cold that space settles into when there's nothing else nearby. And it comes from the oldest event in the history of the observable universe, the Big Bang. In the first moments after the universe began, conditions were unimaginably extreme, temperatures in the trillions of Kelvin. Densities so high that the entire observable universe was compressed into a volume smaller than a proton. In those conditions, even protons and neutrons couldn't exist as stable particles. The universe was a sea of quarks and gluons. As the universe expanded and cooled, quarks combined into protons and neutrons, more cooling. Protons and neutrons combined into helium nuclei and a small amount of lithium nuclei, still hotter than the cores of stars, but already cooling. For the next few 100,000 years, the universe was a plasma, a hot, dense, ionized gas of mostly protons, electrons, and helium nuclei. Radiation was constantly scattered by the free electrons. The universe was completely opaque. No photon could travel more than a short distance before being absorbed or scattered. As a result, you could not see across the early universe any more than you can see through a thick fog. Then, roughly 379,000 years after the Big Bang, the temperature dropped to about 3,000 Kelvin, a threshold. At that temperature, protons and electrons were moving slowly enough that electrostatic attraction could pull them together into neutral hydrogen atoms. When they combined, they stayed combined. The plasma became a neutral gas. A neutral gas does not scatter radiation nearly as effectively as ionized plasma. The universe became transparent. Not gradually, rapidly, over a period of perhaps 100,000 years, which is cosmologically almost instantaneous. The fog lifted, and all the thermal radiation that had been bouncing around in the hot plasma for 379,000 years was suddenly free. It poured outward in every direction, carrying the thermal signature of matter at 3,000 Kelvin. That is the moment the oldest light in the universe was created, not in stars, in the plasma of the early universe. Released when the plasma became transparent, that radiation has been traveling ever since, 13.8 billion years. And during those billions of years, the universe has continued expanding. Space itself has stretched. And here is something that took years to fully understand. When space expands, it stretches the wavelengths of photons traveling through it. It's not that the photons are losing energy to friction or to collisions with matter. Space itself is growing, and the wavelengths grow with it. This stretching of wavelengths is called cosmological redshift. Longer wavelength means lower frequency. Lower frequency means lower energy per photon. Lower energy means lower effective temperature. The radiation that emerged at 3,000 Kelvin has been continuously stretched by cosmic expansion over 13.8 billion years. Today, that same radiation has an effective temperature of 2.7 Kelvin, 1,000 times colder than when it was released, because space has expanded by a factor of about 1,000 since recombination. This radiation fills the entire observable universe. Every direction you look, from anywhere in the cosmos, it's there, coming equally from every direction, at a temperature of 2.7 Kelvin. With tiny temperature fluctuations, differences of 1 part in 100,000, imprinted on it by the slight density variations in the early universe. Those tiny fluctuations, amplified by gravity over billions of years, became the seeds of everything: galaxies, galaxy clusters, the large-scale structure of the universe, the great walls and voids of the cosmic web. All of it grew from variations that are still visible as temperature ripples in the cosmic microwave background. The CMB was predicted theoretically in the 1940s by Ralph Alpha and Robert Herman, working in the context of the developing Big Bang model of cosmology. They combined the known physics of nuclear reactions with models of the early universe to predict the abundances of light elements. And in doing so, they realized that the early universe must have been hot enough to be opaque, and that when it cooled and became transparent, the radiation it released would still be present today, cooled to a low temperature by cosmic expansion. They worked out that if the Big Bang had happened, the universe would have been hot enough in the early moments to produce a specific mix of hydrogen and helium through nuclear reactions. Roughly 75% hydrogen and 25% helium by mass. Exactly what we observe. And the thermal radiation from the early universe should still be present today, cooled to a very low temperature. They calculated a temperature of about 5 Kelvin, remarkably close to the actual value of 2.7, but the prediction wasn't widely noticed. The actual discovery came in 1965, by accident. Arno Penzias and Robert Wilson were engineers at Bell Labs in New Jersey. They were working with a large horn-shaped radio antenna originally built for satellite communications. In the process of calibrating it for use as a radio telescope, they discovered a persistent noise signal they couldn't account for. It came from every direction in the sky. It was the same, regardless of where they pointed the antenna. It didn't vary with the time of day. It didn't vary with the season. They checked everything. They found a pair of pigeons that had nested inside the horn and left behind a coating of what Wilson delicately described as a white dielectric material. They cleaned the antenna thoroughly, removed the pigeons. The noise remained, because it wasn't coming from the antenna. It was coming from everywhere. It was the fossil glow of the Big Bang, cooled over 13.8 billion years to 2.7 Kelvin, the most perfect black-body radiation spectrum ever measured, 2.7 Kelvin. That's the universe's background temperature, the cosmic floor, the minimum temperature any object in the deepest void between galaxies approaches as it radiates heat away, and it can't go below it. Because the CMB is delivering photons from every direction. An object at 2.7 Kelvin would radiate energy at exactly the rate it receives it from the CMB, equilibrium, a flaw that exists everywhere in the observable universe. As the universe continues expanding, the CMB continues to cool. In 1 trillion years, the temperature will be so low it's barely distinguishable from absolute zero. But for now, for the current epoch of the universe, the floor is 2.7 Kelvin. And that's why space is not quite at absolute zero. The universe itself still carries the faint warmth of its own birth. How do we know this so precisely? The CMB is measured in detail by sensitive telescopes and satellites. The first precise measurement of its spectrum came from the COBE satellite, the Cosmic Background Explorer, launched in 1989. COBE found that the CMB spectrum matches a perfect black body at 2.725 Kelvin with extraordinary precision. More perfect than any black body radiation ever produced in a laboratory. The instrument that made this measurement, the far-infrared absolute spectrophotometer, achieved a precision that no ground-based telescope could match, because water vapor in Earth's atmosphere absorbs the frequencies being measured. COBE also detected the tiny temperature fluctuations in the CMB, differences of about 1 part in 100,000 from one direction to another. These fluctuations, the seeds of all structure in the universe, were imprinted in the first fraction of a second after the Big Bang. The WMAP satellite, launched in 2001, mapped these fluctuations in much greater detail. It confirmed the age of the universe at 13.8 billion years. It established that ordinary matter makes up only about 5% of the universe's energy content. Dark matter, about 27%. Dark energy, driving the accelerating expansion, about 68%. All of this encoded in temperature differences of 1 part in 100,000 in an ancient 2.7 Kelvin glow. The Planck satellite, launched in 2009 by the European Space Agency, achieved even finer resolution. It mapped the CMB with such precision that it could distinguish structures on angular scales of about 5 arc-minutes. It refined every parameter of the standard cosmological model, and it confirmed, to extraordinary precision, that the cosmic microwave background temperature is 2.7255 Kelvin. The floor, the baseline, the fossil warmth of the beginning of everything. Different regions of space have different temperatures depending on what surrounds them. The interstellar medium within our galaxy is not a uniform thing. It has distinct phases, different components, each shaped by different physical processes. The coldest and densest regions are the molecular clouds. Giant clouds of gas and dust, primarily molecular hydrogen, where new stars form. Deep inside the densest cores of these clouds, temperatures can fall below 10 Kelvin, as low as a few Kelvin in some cases, just barely above the cosmic microwave background floor. These clouds are the stellar nurseries of the galaxy. The giant molecular cloud complex in Orion, visible as the Orion Nebula and surrounding region, is one of the closest to us. It's about 1,300 light-years away. Its coldest, densest cores are at temperatures of 10 to 20 Kelvin. The darkness and cold are necessary for star formation. In those cold, dense regions, gas clouds can collapse under their own gravity without being disrupted by thermal pressure. Too warm, and the gas pressure prevents the collapse. Just cold and dense enough, and gravity wins. A new star ignites. The warm neutral medium is more diffuse. Neutral hydrogen spread across much larger volumes, warmed by the general radiation field of the galaxy, by cosmic rays, and by radiation from nearby stars. Temperatures of 6,000 to 10,000 Kelvin. The warm ionized medium is hydrogen that has been ionized by intense ultraviolet radiation from hot, massive, young stars. These regions glow in emission line light. There, the glowing nebulae, visible through telescopes, the Orion Nebula, the Lagoon Nebula, the Eagle Nebula, all of them warm, ionized, medium regions, lit up by the radiation of young, massive stars embedded in them. Temperatures around 8,000 Kelvin. And the hot, ionized medium is the most tenuous and most widespread component of all. Temperatures between 100,000 and 1,000,000 Kelvin, heated by the shock waves from supernova explosions. When a massive star reaches the end of its life and explodes, it releases enormous energy into the surrounding interstellar gas. The shock wave heats the gas to millions of Kelvin, drives it outward, creates an expanding bubble of hot, thin plasma. Our galaxy produces roughly 1 or 2 supernovae per century. Over billions of years, these explosions have heated and shaped a significant fraction of the interstellar medium. The hot, ionized medium fills a large fraction of the galaxy's volume. The Milky Way galaxy itself, roughly 100,000 light-years in diameter, is a disk of stars, gas, and dust rotating around a central region containing the supermassive black hole Sagittarius A. The stars and denser gas are concentrated in the disk. But the hot, ionized medium extends far above and below the disk as well. forming a kind of hot, tenuous halo around the galaxy. Temperatures throughout this extended medium reaching hundreds of thousands of Kelvin, but densities so low that the heat content is negligible. A spacecraft traversing from one side of the galaxy to the other, far from any star, would spend most of that journey in this hot, tenuous gas. And throughout, it would be cooling, radiating heat away, approaching the cosmic microwave background temperature, because the gas, for all its extreme temperature, cannot warm it. There simply aren't enough particles. But it's thin. So thin that despite its extreme temperature, it carries almost no heat. A spacecraft traveling through the hot ionized medium would not warm up from it. It would cool down. Because even at 1,000,000 Kelvin, when there are so few particles, the rate at which they deliver energy to any surface is smaller than the rate at which that surface radiates energy away into the void. The region around our solar system has its own interesting thermal history. Within a few hundred light-years of the Sun, we're situated inside what's called the local bubble, a roughly ellipsoidal region of hot, thin interstellar gas. Temperatures around 1,000,000 Kelvin, but density extraordinarily low, estimated to have been evacuated and heated by a series of supernova explosions over the last few million years. Exploding stars that blew their gas outward, carving out this bubble of hot emptiness in which our solar system currently travels. The boundary of the local bubble, where it interfaces with the surrounding denser molecular gas, is visible as a ring of star-forming regions. The Scorpius-Centaurus association of young stars, the Ophiuchus molecular cloud, the Taurus molecular cloud, all of them at the edge of this bubble, carved by ancient stellar explosions. Inside the bubble, temperatures are around 1,000,000 Kelvin, and the heat content of those 1,000,000 Kelvin particles is essentially zero. The same story. Always the same story. High temperature. Almost nothing there. There's one more region worth noting in this picture. The space between galaxies. The intergalactic medium. If the interstellar medium is sparse, the intergalactic medium is almost incomprehensibly more so. In the vast voids between galaxy clusters, the average density of matter drops to roughly 1 hydrogen atom per cubic meter. Not 1 per cubic centimeter, 1 per cubic meter. A cubic meter of intergalactic void contains, on average, a single atom. At those densities, the concept of a gas temperature barely applies in any meaningful way. The temperature of individual atoms in this region is thought to be in the range of 100,000 to 1,000,000 Kelvin, heated by the shock waves from galaxy formation and the radiation of quasars and active galaxies. But the heat content per unit volume is so infinitesimal that it defies description. A cubic meter of the hottest intergalactic void contains less total thermal energy than an ice cube at -200 degrees Celsius. The temperature is high. The heat is essentially nothing. The cosmic web, the large-scale structure of filaments and voids that connects galaxies into a vast network, shows this at its most extreme. The filaments, where galaxies cluster and gas is relatively dense by intergalactic standards, are warm. The voids in between, where matter is so sparse that galaxies rarely exist, are the coldest volumes in the universe, approaching the CMB temperature, 2.7 Kelvin. The absolute floor. Waiting everywhere, that matter is absent and stars are far away. The equilibrium temperature any object reaches in space depends on a single balance: how much energy the object absorbs from incoming radiation versus how much it emits as outgoing thermal radiation. This is radiative equilibrium. No conduction, no convection, just radiation in and radiation out. The relationship between temperature and emitted radiation is the Stefan-Boltzmann law, named after Joseph Stefan, who discovered the empirical relationship in 1879, and Ludwig Boltzmann, who derived it theoretically from thermodynamic principles in 1884. The law states that the power radiated per unit area by a perfect emitter, called a black body, is equal to the Stefan-Boltzmann constant multiplied by the fourth power of the absolute temperature. The Stefan-Boltzmann constant has a value of about 5.67 times 10 to the power of minus 8 watts per square meter per Kelvin to the fourth power. The fourth power is what matters. If you double the temperature of an object, it doesn't radiate twice as much power. It radiates 2 to the fourth power, which is 16 times as much. Triple the temperature, and it radiates 81 times as much. This steep dependence has enormous consequences. Hot objects cool rapidly because they radiate so intensely. Cool objects cool slowly because their radiated power is low. And, as an object approaches the ambient background temperature, the rate of cooling approaches zero. It asymptotically approaches the background temperature, but never falls below it. For an object in deep intergalactic space, far from all sources of light, the background is the CMB at 2.7 Kelvin. The object cools toward that. For an object in the inner solar system, the dominant radiation input is from the sun. The object absorbs solar radiation, heats up. As its temperature rises, it radiates more and more energy. Eventually, it reaches a temperature where outgoing radiation exactly matches incoming. Radiative equilibrium. For a perfectly absorbing object at Earth's distance from the Sun, this equilibrium temperature is about 278 Kelvin, just below the freezing point of water. Earth's actual average surface temperature is about 288 Kelvin, 10 degrees warmer. The difference is the greenhouse effect. Earth's atmosphere absorbs some of the infrared radiation that the surface emits upward, and re-radiates some of that energy back toward the surface. This reduces the rate at which the surface loses heat, warms the surface by about 33 degrees Celsius compared to what it would be without the atmosphere, making the difference between a planet with liquid water and one locked in permanent ice. Venus provides a sobering illustration of the greenhouse effect taken to an extreme. Venus is closer to the Sun than Earth, at about 70% of Earth's distance. Based purely on distance, its equilibrium temperature without an atmosphere would be about 330 Kelvin. Warm, but not dramatically so. The actual surface temperature of Venus is around 735 Kelvin, 462 degrees Celsius. Hot enough to melt lead. Hot enough that the Venera spacecraft that the Soviet Union landed on Venus's surface survived for less than 2 hours before being destroyed by the extreme temperature and pressure. The reason Venus is so extreme is its atmosphere, a thick blanket of carbon dioxide, with an atmospheric pressure at the surface about 90 times higher than Earth's sea level pressure. The dense carbon dioxide atmosphere is extremely effective at trapping infrared radiation. It creates a greenhouse effect far more powerful than Earth's. Heat that would otherwise radiate away into space is trapped. The surface temperature climbs far above what the Sun alone would produce. The greenhouse effect that saves Earth from being frozen solid has, on Venus, turned that planet into an oven. Mars, shows the other extreme. Mars is about 1.5 times Earth's distance from the Sun. It receives about 43% as much solar radiation per unit area. Its equilibrium temperature, without an atmosphere, would be about 210 Kelvin, minus 63 degrees Celsius. Mars does have an atmosphere, but it's extremely thin, about 1% of Earth's atmospheric pressure, almost entirely carbon dioxide, but too thin to create a significant greenhouse effect. Mars's average surface temperature is about 210 Kelvin, minus 63 degrees Celsius. Essentially, the theoretical equilibrium temperature, because the thin atmosphere barely changes things. Earth, Venus, and Mars. 3 planets at different distances from the same sun. 3 dramatically different temperatures, driven almost entirely by their different atmospheres, not by their distance, not by the sun's radiation alone, by what happens to that radiation after it arrives, whether it's reflected, whether it's absorbed, whether the heat can escape or is trapped. The Moon provides the most direct illustration of the physics without any complication from an atmosphere. No atmosphere. No greenhouse effect. No convection. No conduction through air. Just radiation in and radiation out. The lunar surface, in full sunlight, absorbs solar radiation. It heats up to roughly 400 Kelvin, about 127 degrees Celsius. The lunar surface on the night side, facing away from the sun, has nothing to retain its heat. It radiates thermal energy outward into space. The temperature drops to roughly 100 Kelvin, about minus 173 degrees Celsius. A difference of 300 degrees Celsius between the day side and the night side of the same world, separated only by the line between sunlight and shadow. No gradual transition, no buffer, just light on one side and void on the other. Some craters near the lunar poles are permanently shadowed. The geometry of the Moon's orbital tilt means the sun never rises high enough to illuminate the floors of certain deep polar craters. They receive no direct solar radiation. They have no atmosphere to carry heat in from the sunlit regions. Their temperature is measured at below 40 Kelvin, minus 230 degrees Celsius. Water ice has been found in these craters. Ancient ice, billions of years old, preserved in permanent shadow while the nearby sunlit surface reaches 127 degrees. Mercury shows the same phenomenon more dramatically. Mercury is the closest planet to the Sun. At its perihelion, its closest approach to the Sun, it receives roughly 10 times more solar radiation per square meter than Earth does. In direct sunlight, Mercury's surface reaches about 700 Kelvin, 427 degrees Celsius, enough to melt zinc, nearly enough to melt lead. Mercury's night side, with no atmosphere and no mechanism to retain or distribute heat, drops to below 100 Kelvin, minus 173 degrees Celsius. The same temperature as the permanently shadowed lunar craters. And in those permanently shadowed polar craters on Mercury, temperatures measured by the Messenger spacecraft and confirmed by radar observations from Earth have been found to be extraordinarily low, below 100 Kelvin, perhaps as low as 50 Kelvin in the most shadowed regions. Cold enough that water ice, ammonia ice, and other volatile compounds deposited there by ancient comets have been preserved for billions of years. Hot enough on the sunlit side to melt metals. cold enough in shadow to preserve ancient ice. Same planet. Just different geometry between surfaces and sunlight. The same principle applies to every airless body in the solar system. Vesta, one of the largest asteroids, has surface temperatures that swing between roughly -20 degrees Celsius in sunlight and -150 degrees in shadow. Ceres, the dwarf planet in the asteroid belt, is slightly farther from the Sun and correspondingly colder. Its permanently shadowed polar craters have temperatures below -170 degrees Celsius. Even at much closer distances to the Sun than Earth, any surface without the buffer of an atmosphere experiences these extreme swings. Comets illustrate this beautifully. When a comet approaches the inner solar system, the sunlit surface heats dramatically. Water, ice, and other volatiles vaporize, creating the comet's glowing tail. The nucleus, the solid rocky body beneath the sublimating ice, can reach temperatures of around 40 or 50 degrees Celsius on the sunlit side, while the night side remains at temperatures close to the cosmic background. On the same object, at the same moment, the same physics every time. Photons land. Heat accumulates. Photons don't land. Heat dissipates into the void. The boundary between hot and cold is always and only the boundary between light and shadow. Nothing else. No human experience of this is more direct than what astronauts face in orbit. The International Space Station orbits Earth at an altitude of roughly 400 kilometers. Each orbit takes about 90 minutes. Each 90 minutes, the station crosses from full sunlight into Earth's shadow and back. Every 90 minutes, the thermal environment changes radically. In sunlight, at 1,361 watts per square meter, the station's external surfaces absorb solar radiation. Those surfaces can exceed 120 degrees Celsius. In shadow, with solar input gone, the surfaces radiate heat outward into space. Temperatures drop. Some external surfaces reach -150 degrees Celsius or lower. A swing of nearly 300 degrees in the same object over the course of 90 minutes. On Earth, moving from sunlight to shadow doesn't cause anything like this. The air around you, warmed by convection and conduction, maintains a relatively uniform temperature. The shade of a tree or a building is maybe 5 or 10 degrees cooler than direct sunlight. In space, there is no air. The shade of Earth's shadow is not 5 degrees cooler. It's hundreds of degrees cooler. The shadow is where the sun's photons don't reach. And where photons don't reach, there is nothing to maintain heat. The surface radiates away into the void. Temperature drops. This engineering challenge is one of the most demanding in all of spacecraft design. The International Space Station uses an elaborate, active thermal control system. 2 fluid loops circulate inside the pressurized modules. An internal loop uses water as the working fluid. It collects heat from the station's electronics, from the crew, from all the heat-generating systems inside. It carries that heat to interface heat exchangers. There, it transfers the heat to an external loop. The external loop uses ammonia as the working fluid. Ammonia is chosen because it remains liquid at the extremely low temperatures encountered in shadow phases. The ammonia carries the heat outward to the radiator panels. Those large white panels extending from the station's main truss structure. Each panel is designed to radiate heat efficiently as infrared radiation into space. The system can move about 70 kilowatts of heat away from the station continuously. That's roughly the electrical output of about 20 average homes. 70 kilowatts of heat that has to be shed continuously. Because in space, all heat leaves only through radiation. This fact shaped the entire history of human spaceflight. In the early 1960s, engineers designing the Mercury capsules discovered quickly that heat management was among the most critical challenges they faced. The first American astronauts in orbit discovered that temperature swings inside their capsules could be extreme if the orientation wasn't carefully managed. Too much sunlight on one surface, and it would heat dangerously. Too long in shadow, and the cold became a problem. Every subsequent spacecraft program has had to solve increasingly complex versions of the same fundamental problem. The Apollo lunar surface suits were marvels of thermal engineering, multiple layers of reflective insulation, careful selection of outer surface materials to balance solar absorption and infrared emission, and the same liquid cooling system that astronauts use today. The astronauts walking on the lunar surface were doing so in an environment where the sunlit regolith beside them was at 127 degrees Celsius, and the shadow of a rock a meter away was at -70 degrees Celsius. The suit had to manage that transition seamlessly, because in that environment there was no air to moderate anything, just radiation, and the physics of where photons fell. During spacewalks, the challenge is solved differently. Spacesuit thermal management. The outer surface of a modern suit has multiple layers with carefully chosen optical properties. The outermost layer is white, chosen specifically to reflect as much visible sunlight as possible and reduce heat absorption. Inner layers are aluminized, reflecting infrared radiation. The suit contains a liquid cooling and ventilation garment worn directly against the astronaut's skin. Hundreds of meters of fine plastic tubing woven into a tight garment like long underwear. Water flows through the tubing. The water absorbs heat from the astronaut's body generated by the physical work of the spacewalk. That heated water flows to a device called a sublimator. The sublimator vents the water into the vacuum of space through a porous plate. As the water passes through the plate, it immediately turns from liquid to vapor. The phase change from liquid to gas absorbs an enormous amount of energy. That energy comes from the warm water. The water releases heat as it evaporates, and the vapor carries that heat away into space. The result is cooled water flowing back to the garment, a constant cooling cycle. Without this system, an astronaut doing physical work during a spacewalk would heat up within minutes. The suit can't convect or conduct heat away. Radiation alone is not fast enough to handle the metabolic heat generated by vigorous activity. Active cooling is mandatory. All of this engineering complexity, from the space station's radiator panels to the sublimator in a spacesuit, exists because of one simple physical fact. In space, radiation is the only mechanism for exchanging heat with the environment, and radiation follows the strict geometry of where photons fall. Heat accumulates in the light. Cold waits in the shadow, with nothing in between to soften the transition. The thermal management challenges of space travel become more severe the farther you go from Earth. In low Earth orbit, the space station at least has Earth's infrared radiation warming its underside slightly. Earth is a warm body at roughly 255 Kelvin, and it radiates infrared heat upward. The station absorbs some of this. It moderates the extremes slightly. In deep space, beyond the planets, there's no warm body nearby. The only background radiation is the CMB at 2.7 Kelvin. Every surface the spacecraft has radiates outward into a 2.7 Kelvin environment. The spacecraft's internal heat generation must be carefully managed. Waste heat from reactors or electronics must be dumped through radiators before it builds up to dangerous levels. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, used radioisotope thermoelectric generators as its power source. The generators produce both electricity and waste heat. At Saturn's distance from the Sun, solar panels produce barely enough power to run a flashlight. Cassini had to manage its waste heat carefully with radiators, pointing them toward cold space to dump heat efficiently, managing which surfaces faced the Sun and which faced the cold void. A constant thermal ballet across 14 years of Saturn exploration. The New Horizons spacecraft, which flew past Pluto in 2015, faced similar challenges. At Pluto's distance, the Sun delivers about 1 watt per square meter, less than a small nightlight. The spacecraft had to conserve heat from its radioisotope generator while also managing temperature swings as it rotated. Every mission to the outer solar system confronts the same reality. Space is cold, getting colder the farther you go. And managing heat in the cold void requires engineering that must account for every watt of energy gained and lost through radiation. Because radiation is the only game in town. To see the full picture clearly, follow the energy from the Sun's core all the way out to interstellar space. In the Sun's core, temperature is about 15 million Kelvin. Hydrogen nuclei, bare protons, are fusing into helium nuclei. This process requires temperatures high enough that the thermal motion of protons is energetic enough to bring them close enough together for the strong nuclear force to take over from the electrostatic repulsion that normally keeps them apart. At 15 million Kelvin, a small fraction of proton encounters result in fusion, releasing energy, according to E equals mc squared, converting a small amount of mass into an enormous amount of energy. Every second, the Sun converts about 4 million tons of matter directly into energy. 4 billion kilograms, gone, converted into photons and neutrinos. 4 million tons per second for 4.5 billion years. The cumulative total is staggering. But the Sun has used only a tiny fraction of its total fuel. It has enough hydrogen remaining to continue at roughly this rate for another 5 billion years. The neutrinos pass through the Sun essentially without interacting with anything and escape at the speed of light. About 2% of the Sun's total energy output leaves as neutrinos. Trillions of them stream through your body every second. You never feel them. The photons are different. They carry the remaining 98% of the energy, but they don't escape immediately. The solar interior is extraordinarily dense. The plasma in the Sun's core is so dense that a photon travels, on average, less than a centimeter before being absorbed by an ion, then re-emitted in a completely random direction, then absorbed again almost immediately. Re-emitted, absorbed, re-emitted. This process is called a random walk. Each step is tiny. Each step goes in a random direction. The photon bounces around the solar interior. It makes almost no net progress outward with each bounce. Between each absorption and re-emission, the photon's energy has been transferred to the absorbing particle, and a new photon of slightly different energy is emitted. The original photon identity is lost. What survives is the energy, bouncing from particle to particle in an enormous random walk, rising slightly on average because it was generated in the denser core and is working its way toward the less dense outer layers. But slowly, very slowly. The time this random walk takes to transport energy from the core to the surface is estimated at somewhere between 10,000 and 100,000 years. The energy reaching Earth from the Sun today was generated deep in the solar core long before human civilization existed. It has been diffusing outward through the Sun ever since. When energy finally works its way to the outer third of the Sun's radius, where the plasma is less dense, convection takes over. Hot plasma rises from the depths, carries energy to the surface, releases it as radiation. The cooled plasma descends. The process repeats. When energy reaches the photosphere, the thin layer from which light can finally escape without being immediately reabsorbed, photons leave the Sun in every direction at 300,000 kilometers per second. 8 minutes and 20 seconds later, they cross Earth's orbit. A fraction of them hit Earth. Most continue outward, through the asteroid belt, past Jupiter, past Saturn, past Uranus, past Neptune, through the Kuiper belt, the region of icy bodies beyond Neptune that includes Pluto and thousands of similar worlds, through the termination shock where the solar wind slows abruptly, through the heliosheath, the turbulent outer region of the Sun's influence, through the heliopause, the boundary beyond which the interstellar medium dominates. Voyager 1 crossed this boundary in 2012, about 18 billion kilometers from the Sun. The probe is now deeper into interstellar space than any other human-made object, still transmitting. Its radio signals now take more than 22 hours to travel from the probe to Earth at the speed of light. Beyond the heliopause, the photons that started on the Sun's surface travel through the interstellar medium, where there is, on average, roughly 1 hydrogen atom per cubic centimeter, where the chance of a photon hitting anything in a meaningful distance is very small, where photons may travel for light years before encountering a single particle. And through that entire journey, from the Sun's photosphere to the edge of the heliosphere, to interstellar space, to the vast dark between the stars, those photons do not warm the space they pass through. They can't. The space is not a substance. Vacuum cannot absorb electromagnetic energy. The photons carry their energy intact through all of it, depositing it only if and when they finally strike something. Something with matter. Something that can absorb a photon and convert its energy into heat. Everything else, every cubic meter of space between the source and that eventual destination, is unchanged. Cold, dark, undisturbed by the energy flowing through it. The answer to the question is now clear. We started with something that looked like a paradox. The Sun is hot. Space is cold. How can those two things be simultaneously true? The answer is that they're not in contradiction. They're perfectly consistent, because the question was based on a misunderstanding of how heat actually travels. And now, that misunderstanding is resolved. The Sun is hot because nuclear fusion in its core generates an enormous surplus of energy. That energy works its way outward through the solar interior over tens of thousands of years. It reaches the surface. It leaves as radiation. Space stays cold because everything that could warm it fails. Conduction fails because space has almost no particles to form a chain of collisions. Tap a metal rod and the vibration travels from atom to atom. In space, there's nothing to tap and almost nothing for the tap to travel through. Conduction fails completely. Convection fails because space has no fluid, no gas to rise, no liquid to circulate, no medium to carry bulk thermal energy from one place to another. Convection fails. Radiation crosses the void at the speed of light, but it doesn't warm the void because the void can't absorb it. It warms whatever it hits, not the space between the source and the target. The sparse particles in space, the solar wind, the interstellar medium, are technically at high temperatures in some regions. But temperature without density is just the speed of almost no particles. And almost no particles can't deliver meaningful heat to anything. The cosmic microwave background at 2.7 Kelvin sets the floor. The remnant warmth of the universe's own beginning. The temperature toward which everything in the deep void tends. Just barely above absolute zero, and not climbing, not warming, not trending toward the temperature of the nearest star. Holding steady at 2.7 Kelvin, as it always has, as it always will. The sun is hot and space is cold. Two facts, not in conflict, not contradictory, both following from the same underlying physics, both facts exactly what the physics demands. The resolution of the paradox is also, in a sense, a resolution of a deeper intuition about how the universe is structured. We tend to think of the universe as a warm, active place, full of light, full of energy, full of stars, blazing in every direction. And there is some truth to that. The universe does contain an enormous amount of light and energy. The CMB alone carries about 400 photons per cubic centimeter across the entire observable universe. That's a lot of photons. But 400 photons per cubic centimeter at 2.7 Kelvin represents an almost unimaginably small amount of energy. And visible light from stars, while it's enough to light the night sky on Earth, represents an even smaller fraction of the total volume of space when you account for how spread out that light is. Most of the universe, by volume, is a dark, cold, near-empty void. The stars, brilliant as they are separated by distances so enormous that the average energy density of starlight across the universe is extraordinarily low, far lower than the energy density of sunlight at Earth's surface, far lower than the energy density of the CMB. The universe is mostly empty, mostly dark, and mostly cold. The bright, warm, active places, the surfaces of stars, the heated atmospheres of planets, the glowing nebulae of star-forming regions are tiny exceptions. Tiny islands of heat and light in an ocean of cold and dark. And we live on one of those exceptions. On the surface of a planet whose atmosphere traps and holds and redistributes the heat from a nearby star. An island of warmth in the cold. There's a perspective in all of this that goes beyond the technical. Something about what it tells us, about where we are. Right now, you're sitting on a planet wrapped in a thin layer of gas. That gas layer, the atmosphere, is doing something for you that is never celebrated and never noticed. It's catching the sun's radiation, absorbing it, holding it in the thermal motion of atmospheric molecules, distributing it through convection and weather from the warm tropics to the cold poles, retaining enough of the outgoing infrared through the greenhouse effect to maintain the surface at temperatures where liquid water is stable, where organic chemistry can proceed. where life can exist. Without that atmosphere, Earth would behave like the moon. Scorching heat in sunlight, near absolute zero in shadow. Every day, every night, no middle ground, no moderation, no gentle evening temperature drop, just the brutal physics of radiation and vacuum. The atmosphere is an enormous, self-sustaining thermal buffer, running on solar energy, without maintenance, without interruption, for 4 billion years, day and night, across every season, across ice ages and warm periods, redistributing heat with every breath of wind, every ocean current, every rain cloud, never pausing, never failing, for 4 billion years, keeping the surface in the habitable range that allows water to stay liquid, that allows proteins to fold properly, that allows chemistry to be complex enough to produce and sustain life. We take it completely for granted. We have never known anything else. But space shows you very clearly what the alternative is. Blazing where photons fall, frozen where they don't. The line between the two as sharp as the edge of a shadow, with nothing to smooth the transition. Earth is remarkable, not just because it has liquid water, not just because it has oxygen. It's remarkable because it has a mechanism for holding heat, for redistributing warmth, for maintaining the narrow range of conditions where biology works. And that mechanism, that thin, fragile, self-sustaining layer of gas, is the only reason sunlight feels warm instead of simply bright. The universe doesn't have temperature. It has objects at temperature, and between those objects, vast expanses of almost nothing. Vast expanses of near-perfect vacuum, where heat doesn't travel by conduction because there are no particles to conduct it. Where heat doesn't travel by convection because there is no fluid to convect it. Where radiation crosses freely but deposits energy nowhere because there is nothing to absorb it. Just the faint background glow at 2.7 Kelvin. The cosmic floor. The baseline of cold that the entire universe rests against. Nothing doesn't hold heat. Nothing doesn't radiate heat. Nothing is just cold and dark and largely indifferent to the blazing furnaces of stars scattered through it. The sun has been shining for 4.5 billion years. Its photons have crossed the solar system for 4.5 billion years, and interstellar space is still at 2.7 Kelvin, the same temperature as the void between galaxies, the same temperature as the oldest cold in the universe, untouched by 4.5 billion years of solar output. It's not a question of time. It's a question of mechanism. There is no mechanism to warm the void. The photons cross it. The void watches, unchanged, cold, dark, and patient in a way that nothing alive has ever had to be. This is the universe's natural state, not a temporary condition waiting to resolve. The permanent condition of most of space, from the beginning of time until the last stars burn out. Cold, empty, and trending colder. As the universe expands, as the cosmic microwave background redshifts to lower and lower energies, as stars eventually exhaust their fuel, as the universe approaches thermodynamic equilibrium. The warmth we experience here is a brief, local exception in a cosmos trending inexorably toward cold. Most of it, by volume, is cold, empty, dark. The stars are the exception. Bright, hot islands of nuclear fire scattered through an ocean of cold. Each one a local source of radiation that warms the space and surfaces around it, but only locally. Only where those photons actually land. Only for as far as the inverse square law lets the energy reach before it dilutes below any meaningful threshold. And we live next to one of them, on a rock with an atmosphere that catches its heat and holds it and circulates it and turns it into the ordinary warmth of an ordinary afternoon. Which means every time you feel sunlight on your face, you're experiencing the exception, the rare thing. Because the universe is mostly not this. Mostly, the universe is cold. Mostly, the universe is dark. Mostly, the universe is the 2.7 Kelvin background glow of something that happened 13.8 billion years ago. Slowly fading, still present. Still the baseline against which all warmth is measured. And we live in the warm corner, next to a star, wrapped in an atmosphere. On the right side of the physics. That phrasing might sound like luck, but it's not random. The atmosphere is the way it is because of the specific history of this planet. Because of the distance from the sun that settled into over billions of years of orbital dynamics. Because of the size of the planet that determines how much gravity it has to retain atmospheric gases. Because of the volcanic activity that produced the early atmosphere. Because of the biological evolution that transformed that atmosphere, adding oxygen, regulating carbon dioxide, all of it connected. All of it contributing to the precise thermal envelope we live inside. The 2.7 Kelvin of the cosmic background is not a distant abstraction. It's the baseline that your atmosphere is working against every second of every day. The difference between the temperature of your body and the temperature of the void is maintained entirely by the sun's radiation and the atmosphere's ability to hold some of it here. Remove the sun, and the atmosphere gradually cools toward 2.7 Kelvin. Remove the atmosphere, and the surface temperature swings between extremes with every rotation. The narrow range where you exist, the narrow range where liquid water is stable and biology is possible, is maintained by the interaction of a star and a thin layer of gas. Neither is sufficient alone. Both together make the universe habitable, at least in this one small corner. And that corner is where we live, where we've always lived, where every living thing that has ever existed has lived. Every species, every ecosystem, every moment of biological life in the 4 billion year history of this planet, all of it in the warm exception, in the light, in the atmosphere's embrace. With the cold of the universe held at bay by nothing more than distance from a star and a thin layer of gas. That's all it takes. That's all it has ever taken. No more, no less. The star, the distance, the gas, the 4 billion years of stability, the thin, invisible layer between us and the void. Good night. Not a coincidence that you're warm right now. Not a given. Not a guarantee anywhere else in the universe. Just the physics working out in your favor. Here, on this particular rock, next to this particular star. And the next time sunlight warms your face, remember what it actually crossed to get there. 150 million kilometers of cold, empty nothing. Through the vacuum. Through the near absolute zero. Through the void that has been cold for 13.8 billion years and will stay cold for billions more. through space that was cold before Earth existed, before the sun ignited, before any of this was here, through the space that all the sun's photons have been crossing for 4.5 billion years without warming a single cubic meter of it, and then arrived, with all its energy intact, exactly here, and warmed you, which means the universe made an exception for you today.